this one, and then so it didn't record the audio when I did the brain scanning thing. So I will upload those videos. It's just there's no audio. I could narrate over it, but that would be awkward. Okay, moving on. So if you remember what the shape of the brain is, does that help you? Yes, I'm not going to make you label a diagram because, well, physio has to. But the cool thing for physio, what they don't know is, as I'm making models of the brain, I'm going to be taking pictures of it. Because I stick it up on the whiteboard as I make the models. And I'm going to take a picture of it. And guess what they have to label? The one we made in class. And I might even go around and take pictures of different people who have very good ones and use those as the images that they have to identify. We'll see how it goes. Last year I had the exam scores from last year from that same test, and so we'll see how it goes this year for them. Okay, did I give you these yet? Okay, so this is actually a real dissected brain. Okay, this one is my mother-in-law, was still in her head at the time, and this is a model. Okay, so what I wanted to kind of show you just kind of the surface and looking at the brain, and we're going to go through the parts today. The goal is either today at the end of class or at the beginning of next class, we're going to pretend we are a brain. I'm going to give all of you everybody's going to get a different part of the brain, and you're going to have to try to change behavior. And so you're all going to try to influence the person that is in charge of making behavior. It'll be awesome and awful at the same time. Okay, you start to realize how this brain works. Okay, so now let's look at this really quickly. Can you use the lights up so we can see the resolution better? And then I'll draw some stuff. So can you slide back? Thank you. Whoa, I hit them both up. Why not? Let it roll. Yeah. Okay. Okay, so first of all, so this is, what's this hole on the side of your head? That's from here. You'll see your cheek go up through. So this is the skull. In an MRI, what is black on an MRI? Fluid. Fluid. So the thing that reflects least from an MRI is the more watery type stuff. The harder the substance, the whiter it is. So like bone is bright white. Okay, tendons are gray because they're not as hard as bones, but they're harder. Okay, so as we dig in through my mother-in-law's brain here, I want you to pay attention to something. What are all these dark lines? They're grooves. The brain is covered with these bumps and grooves. And they go all the way down. You can see that this is just a slice. You cross your ear, you can see her inner ear right in here. And you get to see the space behind your ear and your skull. But you notice that it's surrounded by fluid, and the fluid flows throughout the entire brain. So it's cerebral spinal fluid. And some of these bumps and grooves, like if you pay attention to this one that goes across here, that's the same one that goes across here. That's this called Sylvanian fissure. But that groove goes all the way through the center of the brain. So as we keep cutting slices off the brain, you can see that groove goes all the way down to the middle. And you can actually start to realize that this part of the brain up here, the front part, is not connected to the side part, except when we get way back in the center in here. So this is again towards the side. So right now we're almost at the edge of this little part right here called the cerebellum, which we'll talk about. Let me rotate that so you can see. Stop. Start it. Okay. I can stop it. There you go. Okay. So we're just barely cutting the surface right here because we can barely start to see this little part right here. We're right about here in the brain. Just to give a perspective of where we are. Okay. This is what I do in the afternoon when I can't think, so I make animation. Okay. So now you can see that little chunk at the bottom really nicely. Now we're getting closer to the center. Notice how some of these grooves go all the way down. Some of these grooves go all the way down to the center of the brain. So that the brain has a tremendous amount of surface area.
Okay, so then we get to the center. Now here we slice the dissected brain into the center. And here we start to see my mother-in-law's representation of this part of the brain. How come this brain looks different than my mother-in-law's brain?
There's no fluid here, so this is allowed to kind of expand out a little bit. So when you get a brain like this,
I have a rat brain in my office where we did this. Not human yet. But you actually, apologize for the rat lovers in here, but you stick a large needle into the aorta, the large valve of the heart, and you flush the entire brain with saline. So saline is like the stuff that I was squirting on the electrode. And it fills the entire brain with clear fluid, not bloody fluid. So far, so good. Then, once it runs clear, then you actually put a chemical called glutaraldehyde in it. And glutaraldehyde takes the fatty tissue of the brain and changes it into plastic. Anyone seen the Bodies Alive exhibit? It's creepy. But what they do is they soak bodies or they perfuse bodies in this fluid that changes the cells from the fat in the cells to plastic. And so you have these exact replicas of people, except they are plastic, all the way down at the cellular level. So if you keep slicing it and looking at it, it's all plastic, but it's real. It's like a real, it's kind of like a fossil, except plastic fossil. No. So when we look at this, you can start to see in the real brain, it's a little bit different shape. Now notice this is the part called cerebellum, we'll talk about those in a minute. You notice it's really folded over here, but you don't see that here. That's because this is not smoothed inside of someone's skull. Does this change shape as you get older? Yes. If you have a concussion, this changes. Notice that there's a big bundle of chunks right here. This chunk right here, what color is it? Well, no, this is the black spot. This is the white. So that white is basically where the two sides are connected. I'll show you another picture in a minute. The two sides are not connected. The left and right part of the brain are completely separate, except for right here. This is the only place where the two sides are connected. So if you notice, like this right here looks just like the surface of the brain. Because you see how this is the surface of the brain? The only part of the brain wraps all the way around, it only connects right in the center. There are some people who don't have this part of the brain. And as a result, they have two separate cells in their brain. They have two separate cells. Because what do they have? Two brains. Not two personalities. Personalities on the left side. But they have two separate cells. Ooh, I didn't tell you after class about helping you create electrodes. Okay, not me. That panicked me artist here, sorry. No. Okay, he printed one and it worked, so I need. Okay. Anyway, so. Okay, now getting back. So, the idea of having two separate brains, most of us don't have two separate brains because what do we have? It's not little, this is huge, millions and millions of axons, millions and millions of electrical activities being sent back and forth across the side. Really kind of neat. Okay, notice that the center part right here goes straight down your, it goes all the way down the bottom, the spinal cord. So the center part, the spinal cord goes straight, right up into the center. If you notice, it goes right up into the center, but then it doesn't necessarily connect to every part of the brain. Let me show you this at a different angle here. Go through the other side of her ear. Okay, here's the top-down approach. Her nose would be, she'd be laying on her back, her nose would be facing the ceiling, and then, so as we cut down through the brain, notice that the two sides are only connected at that big fiber that goes back and forth across. Notice that even all the way down the center, except for that fiber that goes across, the two sides are completely separate. Okay? Going to zig all the way down through. Even as we get way down in the bottom of the brain, the left and right side are still not connected. So this part right here, I really love this picture because see this giant bundle of nerves, about as big around as a pencil? That's your eyeball nerve. Come on. So these nerves are coming through
your eyes, you can see they go in, and watch this. Go over here, and then off back here. This eye goes in, crosses over, and goes back here. So anything on this side of the world, what part of the brain do you see it? The other side. Well, there's a reason why. Because if something's flying at you from this side, which hand do you want to use to defend itself? Right side of your brain goes to your left hand. So anything on this side of the world shines on this side of your brain, so it uses this side of your body is used to detect it. So that's why your brain is opposite. Because our eyeballs are lenses, you see. What does a lens do? Reverses an image when it puts it on the brain. Or it's really in the brain. That's two lectures of busy in this point, so we can say yes. So. Okay. So look at what are these little tiny little skeletons in? That's your sinuses. My son's like really congested every morning, unless he remembers to take his allergy pill. Wait a second. If I take my allergy pill, I wake up in the morning and I'm not congested. This morning he didn't blow his nose once on the way to school. Joyous ride to school today. Yeah, did you take your allergy pill last night? Yeah. Yesterday. I'm like, dude, Anyway, sorry. Okay, let me get back to we can cut down through the brain a little bit. Here's my mother-in-law's face. You can actually see her face right here. There's her teeth, there's her nose. Hello, is her eyes open or closed? Closed. You can see her eyelids closed in the MRI machine. What's interesting is you notice that are the sinuses symmetrical on both sides? No. Okay. So the sinuses are not the same on both sides. The reason they're not the same on both sides, whatever side you sleep on, I sleep a lot on my right side, because if I sleep on my left side, I'm, quote, breathing on my wife, and she doesn't like me breathing on her while I sleep. She's like, turn over. So because I sleep on that side, I sleep on this side of the sinuses is more clogged than this side, because I always sleep on that side. So if you look at her sinuses as you go through, you can see that they're not exactly the same on both sides. That's the Mars attack spring. Okay? That they're really different on this side. Okay, I really like this picture, because here's the back of my throat, there's that little dangly thing that hangs down. Look at how different the sinuses are. Huge one on this side, very small one on that side. Okay, second thing, notice that the brain is only connected right here in the center. The brain only connected left and right is right there in the center. That's really important a few minutes later. So everyone should visualize it. There's a really great, anybody can watch a TV show called The True Stories of the ER. It used to be on the Learning Channel. Oh, my wife loves that stuff. She watched the de-scalping episode. Anybody see that one? That people's hairs got caught and stuff, and it pulled their scalp off. And they're like sewing it back on. I'm just running around in small circles, like, you, but I'm interested, but I can't handle it. So, anyway. That's where I was going. So, my favorite one, this is about probably 10 or 15 years ago. A brother shot his other brother in the head with a crossbow. Crossbow. You know, crossbows have short little arrows. And so there was the feathers of the arrow sticking out of his forehead, and a little bump in the back of his hair. So the thing went right through his head. Well, luckily, yeah. But if it hits right in the middle, guess what happens? No. In fact, there's a lot of cases where people have gotten injured in the head. One of them, the guy had the knife stuck on the top of his head. Anybody see that one? Dunk! And it's like, but if the knife isn't that sharp, what will it do to the brain tissue? It moves it out of the way, and the arrow wasn't that sharp. The pipe isn't that sharp. You're much more likely to get injured on something sharp because it cuts as it goes through. Sorry, I'll stop doing that. Okay, let's get past the doom and gloom, and let's get to some brain that we can look at. Okay,
Again, this lecture is typically for my physio class. But what I want to do is I'm going to draw on this. My pen. Can you get the lights back on? Thank you. So what we're going to do is you want to do top down or bottom up for the brain. Okay, so if we go top down, it kind of makes sense, and you slowly build it together. So what is the most human, most complicated part of our brain? What behavior? Let me put it that way. What behavior is the most human and the most complicated? Again, I'm recording this so you can watch this again later on YouTube, like the other two people. Moving on. Ready? Okay, do dogs have memory? Language is pretty damn complex. But what produces language? Yeah. Okay, we can start with language because that is a pretty complicated thing. Dogs don't produce language. But this side of the brain, right on the side here, what color am I working with? Let's make it pretty yellow first. This side of the brain, remember I showed you that fissure that went all the way down through the center of the brain? That's called your temporal lobe. Does that show up at all? No. It's a little bit. Let me make it a slightly darker color. Is that worse? That's okay. Temporal lobe. Okay? The temporal lobe, it's worse, I'm sorry. No, I need to write it down here. It's actually not good to use red because there's a good portion of the population that's red-green colorblind. Some people are embarrassed by it, and then you write red on the screen and people see gray on a white background, they're like, thanks. Yeah. Okay, moving on. So the temporal lobe. The temporal lobe is this whole side lobe here. The temporal lobe is involved with emotions. It's involved with your memory. It's involved with language. This part right here, which I am going to write in a darker color, is called the auditory cortex. This part right here is called the auditory cortex. It's very nifty. What it does is the auditory cortex is where you hear sound here. If you play your guitar, and I can tell whether it's in tune or not. How do I tell if it's in tune or not? My auditory cortex has notes. Everybody's auditory cortex has notes. And that's a simple note. If I say, anybody here really good pitch, a singer or musician of some sort? Someone who has something called perfect pitch, here's the notes as they actually should be. Anybody in here musician? Do you have good pitch? Do you know what I mean when I say perfect pitch? Well, not high, but somebody who is a really perfect pitch will hear a note and you go, that's a little low, wait, okay, that's right. Anybody ever hear a tuning fork? You hit a tuning fork are these metal rods that are in a certain frequency, a certain size. When you vibrate them, they vibrate at a very specific frequency. And what's interesting is that your brain hears a certain set of frequencies. So if a note is not perfectly in pitch, fine, you guys are going to have to suffer with this. Let's go here. Wait for it. I have no idea what this is going to be, but... No. Ooh, the new iPhone things come out today. Okay, ready? Oh, yeah. Oh, this is going to be good. Okay, I'm over this video. Please don't make me watch the rest. Okay, that's a good middle school band. Come on, you're killing me. This is totally not worth it at this point, but it's... Here we go. Wait for it. I hate the internet. What's wrong with that? I was going to say, it's the eyelid of the tiger. It's close. You can recognize the tune, but what's wrong with the notes? Well, okay, so describe what off-key sounds like. If you hear something that is on, if it's on key, so let me play these guys for you really quickly. Where some guys here are good. Berkeley Sax Quintet, sure. Berkeley's got good. There's one guy with like stupid little devil whiskers that was... Nice. So listen to the difference between middle school band and this. What's different? Well, it's actually in tune. But what happens is when somebody else starts playing, the sound gets louder, not noisier. And when everybody adds their sounds together, the pitches of the sounds are all lining up perfectly on different sounds in our quintet. So in the middle school band, one trumpet's on this cell, one trumpet's on that cell. And your brain goes, which cell should I fire? So it fires both. And you hear, but if it's a nice, perfect sound, it's a very pure sound in your head. Now, no matter where you come from in the world, everybody hears the same notes. If you play music for the kids down in Baja, they'll hear the same notes that you all hear. Regardless of their cultural background, regardless of what they've ever heard before, everybody hears the same notes. Really cool. Okay, so, but again, why the auditory cortex in your temporal lobe? So what did we start talking about this for? Language. So what's language? You start sentences so well. Okay, it's not just communication. Because I can flip somebody off, or my daughter, okay? That's communication. But does it convey different meanings? Well, it can if there is intent and purpose behind it. So language is the study of your thoughts. Language is the behavior of your thoughts. Weird, man. So guess what happens also in the temporal lobe? What do? Your temporal lobe is where your thoughts are. Do you think in words? What does Dorian think in? Dorian is not the hurricane, but is his own structure. Does he actually see flashy hands in front of his face? I don't know, I'm not there. Yeah. Then you're in it. But what does he hear? So when he talks to himself, does he hear himself talk? Okay, I'll ask people who are bilingual. Do you think in Spanish? sometimes. So wait, you have two voices in your head? What, are you crazy? No, in fact, you have multiple languages in your head. If you speak more than one language, you emote. Do you have different army speak than normal people speak? So you was in the army. And I have students that were Navy folks. They have Navy language and real people language. Navy language is full of cuss words and lots of acronyms. Real people language, oh, sorry, let me shift gears. If you're speaking to someone else who speaks your language, can you use shortcuts? Yes, but if someone doesn't speak your language, you don't use slang, shortcuts, you use proper language. If you watch the news, they don't use slang on the news. Very rarely, because they speak proper. The best way to learn a language is not by normal conversation, but watch TV, watch the news. It's boring, but what do you get? Proper language. Yeah, and the idea is that, so thinking is in the temporal lobe. Memory is in the temporal lobe. It's actually underneath the temporal lobe. Your fears are in the temporal lobe. They're underneath as well. We'll get to those parts when we slice the brain in half in a few minutes here. But what's interesting all about this is that there's actually an area, it's right about here, it's called Wernicke's area, is where you choose the words that you're trying to communicate. You choose the words that fill in the blank. My friend speaks Farsi. Her mom, and she was born in Iran, and they moved here when she was about 8. She speaks English perfectly well with no accent, but if you're Persian, you have to speak slower. Persian people speak slower. If you speak Arabic, what happens when you get excited? You speak faster. In Persian, when you get angry or upset, you speak even slower. It's interesting. Anyway, but for her, when she's talking with her mom doesn't speak English very well, even though she's been in the United States for 800 years. Because Sherry's my age, so she's been here for 40 years. But her mom doesn't speak English very well, so her mom and her will talk on the phone in Farsi. Farsi, 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 Farsi. And all of a sudden you hear an English word, flop. Cell phone. Farsi, 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 Farsi. And then other English words throws in. How do those English words pop in? Those words evolved after she learned English. And because she's here, does she get to hear what the Farsi word is? No. So she just throws the English word in. And so does her language areas overlap? Yeah, the language areas overlap. And that's what we call people who learn Spanglish. But Spanglish is Spanish and English mixed together. I have a couple of students that speak Tagalog, I don't know. Yeah, they speak a version of Tagalog that's not English, but it's not Filipino. It's both. And it's for people that kind of don't really care about being Filipino, but really don't really care about being in the United States. I need to communicate quickly with my relatives. And it works, sort of, until you try to talk to people who are outside. Anybody seen this horrible movie called Falling in Love? Okay, if anybody wants a good Hallmark movie, my wife watched this weekend. I walked by periodically to see what was going on because the girl that was in it was super cute. But the rest of it was completely lame. But she buys this old rundown inn in New Zealand and goes and renovates it and falls in love with some other New Zealand guy and then ends up moving there. Yeah. I don't know. I walked by and she's really pretty. She's not in this. Okay, I walked back to that. But he keeps using all these stupid, cute terms, like all these colloquial New Zealand terms, like every possible New Zealand slang word he uses in almost every sentence. And it's weird because unless you know what he's talking about, do you have any idea what he's saying? No. But if you're from there, people can have that. Oh, Austin Powers, more cultural relevant example. When Austin Powers is talking to his uncle in Cockney slang. Never mind. Okay. Stay inside. Watch more TV, people. Okay. So, but is thinking the most highest level thing that separates us from most animals? No. It's something else. It's right here. It's your prefrontal cortex. Your prefrontal cortex, that purple does not show up on the black at all. Thanks for telling me as I wrote the entire thing. You can't see that. You're just going to wait for me to notice when I turn around? Thanks. If you can't see something, nobody else can. Okay, let's write prefrontal cortex that I understand. So this part right here is called the prefrontal cortex. This is where your future is. This is the part of your brain where you see what's next. This is the part of the brain when my son was 8 months old does not have. How come he can't move the blanket to get the keys? He doesn't have next. That's what makes us different than most animals. Even some of the best primates, even like chimpanzees, bonobo chimps, which are very similar to us as far as society goes, and a lot of their behavior. But the bonobos don't have as big of a prefrontal cortex. Can a chimpanzee plan for the future? A little bit. They do store food. They do look at social hierarchy. And they do look at relationships. And they do pay attention to a lot of things that are kind of complicated. But they can't plan for next year. They can't look at the weather patterns and go, oh, crap, El Nino's coming. Or right now, so it's nice and cool right now, but we have this thing called the Santa Ana brewing on Thursday. So what does that mean about Friday and Saturday? It's going to be hot. Yeah. So animals that hibernate are really interesting. There's this part of the brain back here we'll get to. Very low in the brain. Those animals don't do it because they don't change their behavior. Go, well, I might as well sleep. It's getting cold out. When the amount of daylight changes, what happens? It changes hormones. And when the hormones change, they start getting sleepy. We studied, there's these little things in psychology, we studied called Siberian hamsters. Siberian hamster is basically a rat with a short tail, so it's cute. But they live up in upper Siberia, in the really frozen areas. So it doesn't make sense for the stupid hamster to go running around in the wintertime, because what will happen to it? It'll die. It just freezes to death. So it burrows down deep into the earth and falls asleep, and its heart rate goes down. Its usually heart rate's around 120, 130. And in the wintertime, it goes down to about 10. But the thing's cold because it's not burning a lot of calories, so it can sleep for 3 or 4 weeks, kind of get up, stretch, walk over to the other side of its den, pee, eat some grasses it has in there, and go back to sleep, and sleep another couple weeks. No problem. So is it doing it consciously or unconsciously? Unconsciously. And there's a part of its brain we'll talk about called the hypothalamus that actually controls that. And you have that too. Why do we always tend to gain weight in the wintertime? Blame the Christian holiday. I don't care if you're Christian or not, but everything yummy comes out around Christmas time. And for some reason, giant buckets of ham. I'm sorry. Now, but again, your metabolisms change. In the wintertime, your metabolism slow down. Summertime, your metabolism speed up. You don't notice it so much in San Diego because it's pretty much all the same here. But man, go north. Just go as far north as Santa Barbara or San Francisco. And do you notice a difference in the season? Yeah. But the further south you go, is there a big difference? Yeah, not at all. Okay, so moving on. So this prefrontal cortex is really important because the lobe that's the biggest in humans is this part right here. It's called the frontal lobe. The frontal lobe is our biggest lobe. The prefrontal cortex is a very large portion of it. This is where behavior comes from. There's a whole area right along here. Actually, I drew on the wrong line. If you're drawing, it won't affect you, but I'll fix it because it's going to bug me. Sorry about that. Okay. Come on. There you go. Okay, so this area right along here is called the motor cortex. The motor cortex is this stripe that I just showed kind of in yellow flashes all the way down here. Motor cortex is interesting because what it controls is muscle tissue. Muscle tissue. So if I take an electric force and point you in the brain right here, what happens? Somewhere where that's connected to will twitch. Every muscle in your body has a neuron in the motor cortex. Where do you think a large portion of the motor cortex is used for? What part of your body? Your hands and your face. Your hands and your face make up about 1/3 of the entire motor cortex. Your leg, little tiny part. Why is your leg a little tiny part? You think that you want a lot of brain to be able to squat. There's not. How many muscles in your leg? 6. How many muscles in your face? Thousands. Because you can, all the different facial expressions, I talked about Rosalind who had a hard time coordinating, because all these little tiny muscles in your lips and your mouth and your tongue all have to move in the right sequence. So there's a huge portion of brain for this. There's something called a Bell's palsy. You talked about that here? Bell's palsy is where you lose the motor ability on one side of your face. Sometimes on both sides, that's really bad. But what happens, the nerve that comes from your face out to your brain, out to your body, gets interrupted for some reason. As the doctors go, we don't know. Well, so a stroke is different. A stroke is when you lose a chunk. So a stroke in any part of the brain disrupts the function of that part of the brain. So if you have a stroke here, all of a sudden you can't move that part at all. But if this part, the parietal lobe is still there, that's right here. So let me change that. So this parietal lobe here, which I'm coloring in blue. Okay? The parietal lobe right in the back, that's where you feel. So in this area that's right next to the motor cortex, like for example, if this part controls the facial muscles, this part controls the feeling on your face. So if you have a stroke and damage the cells here, then you still feel your face. Yes, because if the damage is here, you can't move, but you can still feel. What if you damage here? You can feel, you can't feel, but you can still move. There's a lot of people who have strokes in the parietal lobe, where their hand looks like this. They can move it and move around, but how come they don't have a lot of defined control? Losing the feeling loses control. So our brain works, this is really important, our brain works in feedback. You'll see this when we do our shouting exercise in a little bit. We'll probably get to that fast. I haven't got to the end of that yet. So what happens is if your brain works by feedback, how do you know what to do next? Go back to the prefrontal cortex. How do you know what to do next? Well, you pay attention to what's going on right now. You pay attention to what you're doing right now. You pay attention to what you feel right now. You pay attention to what you're thinking. By changing your thoughts, can it change the way that you feel? Yeah, by changing your thoughts, it changes the way you do things next. There's a really good principle that we need to learn a lot when you have anxiety. It's called the EPIC principle. As the gentleman with the stomach tattoos tried to tell me at the skate park, just peg it, dude. My motto in life, because if I need to go jump off the ramp, I've got the BMX bike now. Now all I need is some shots of testosterone and I'll try it. But In order to go off the top of the ramp, you need to lean back and then push the bike down. Yes, because you're on concrete. And when you're old and you fall down, it hurts. When you're young, you fall down, you go, oh! And then post it on YouTube, and then people comment on it. But when you're old and do it, people walk up, are you okay? Yeah, but I'm wearing a helmet. Okay, right. So, there's that old guy again. Walk away. Okay. So why does the old guy say, just peg it, dude? That makes that dude holding a 40, 9 o'clock in the morning. Turns out, if you stop thinking, does your motor behavior work better? Yeah. Yeah. If you try to think about it, like I'm really working on dropping under the snatch, you pick up the weight, drop underneath it, and like that, right? Really working on that. The problem is if you try to think about it as you're doing it, what happens? You screw up. And if you screw up doing that, there's like 16 different injuries you can get just by stepping the wrong way. There's a really great elbow backwards video that I have that I watched before I did. But I got getting really good at dropping under the clean. So, like next, I have to just get 5 at 225, and then I can say I can do it. I got 5 at 195. Okay. So, just for the record, when I was in college, I could do that stupid. Now I can. When they're like, John, go! My wife's like, shut up. Because you have to make drinking noises. And you drop it in the car. She's like, that's annoying. I'm being everything. So, the parietal lobe talks to the frontal lobe to coordinate behavior and, what's the key word here? But what's the key word that it does? Feedback. So the parietal lobe is our feedback circuit. The parietal lobe is so important for the feedback circuit. Whatever is happening in the body, the parietal lobe gives you feedback to adjust behavior. So, which feedback is the best for humans? What you see, that's your occipital lobe. That's different. That's usually called passing out. No, but so the optic nerve. Remember I showed you the optic nerve? It comes in, it goes right to the center, and then it goes all the way to the back of the brain called the occipital lobe. The way to think about it is light shines on the back of your head. It doesn't do it. It shines on the back of your eye. Don't worry about it. But if the light goes all the way back here, the reason the light goes all the way back here is from back here, occipital lobe is connected. Now it's directly connected to the temporal lobe. It's directly connected to the parietal lobe, but it is not directly connected to the frontal lobe. So what happens is, in order for you to see, to actually understand what you're seeing, like if I make some, if we can pull up some optical illusions here. Optical illusions are really bizarre because you see something that can't exist. Okay, you see things that can't exist. The reason they can't exist is because in reality they aren't there. But they're called illusions because you can trick your occipital lobe into seeing things. The occipital lobe is pretty lame. It doesn't understand the world. It only sees the world. But how come you don't pay attention to the way the world actually is very often? You actually navigate around the world just fine. Anyone ever take the phantom step? I love the phantom step. When you're walking upstairs, you get distracted by the stair you're on. You go off the top. What happened there? It's worse going down. Where you're expecting the next step and you're in the bottom and you're... We have, on our deck, we have, when you walk out the back door, there's one step, and then the deck. And because of the way that it was made, when it's dust out, you cannot see those little 2 steps. So what do people do all the time? Don't step. Just
step off, and then just, one of my daughter's friends crashed, my buddy Leo's crashed 2 or 3 times. He's not the most coordinated person in the world. Just like that. Okay, it's contagious, man. It's going down the road, so you got it first. Okay, so, but the idea that what you see, does that actually change what you do? Yeah, in fact, when you take physio, if you decide, if you like the psych stuff, there's actually areas inside the brain. I'm going to draw these in like a nice purple color. You don't need to know these for intro. But these 2 areas right here constantly are adjusting behavior based on what you see. This is why it's so important for you, if you're any sort of athlete, like a shot putter or something, to get videotape of yourself throwing. Videotape, not mirror. Okay, videotape is really important because if you're watching yourself in a mirror while you're trying to do something, does that change the behavior? Yeah, because you're adjusting it as you're doing it. So it's actual ballerina folks like to adjust themselves in front of a mirror. But in our gym, he refuses to have mirrors because if you're lifting in front of a mirror, you end up changing what you're doing as you're doing it, and you don't learn the proper way. You learn the right way to do things. And so every so often he'll videotape, record us. He'll record us doing stuff to show what we're doing right and how to fix it. But it's much better to learn how to do it right without a mirror. Okay, so now, this is consciousness. But is this all there is in our brain? No. In fact, this is just the surface. This is consciousness. But again, this is the most complicated stuff. Where do you speak? What lobe do you speak from? Not the temporal lobe. Temporal lobe gives you the words. Well, where do you speak from? It's not the prefrontal. Well, hopefully you speak a little bit from the prefrontal cortex. You speak from the frontal lobe. You speak from the frontal lobe. Okay? So this is where talking comes from. So when you speak with an accent, guess what you're doing? You're using the sounds of whatever language you understand best to produce the words from another language. Our Psych Club president, Natalia, it's really funny. When she speaks, she doesn't have much of an accent. But as soon as she speaks Spanish, she sounds very Spanish. Blah, 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 blah. My name is blah, blah, blah. I'm like, I didn't even hear a word of that. How come I couldn't hear a word of what she says? I call her Natalia because it works in my language. Newscasters do this. If you can speak 2 languages, your mouth and your tongue and everything else know the right positions to get in. But if you don't speak 2 languages, you've learned a second language, your mouth and tongue don't know the proper movements to make. Cool. Okay. We're watching a video with my son yesterday, some car video. Okay? And in a stupid little car video, he was looking at, I forget what, like Subarus or something. And the 2 guys that were talking are, oh, they're Canadian. He goes, how do you know? How can you hear someone who's Canadian? So when you talk like Canadian, you have to speak French, but with make French sounds with an English word. And so you can hear the Canadian because they pause in different places in sentences, just like you're speaking French. And so if you start speaking that way, people think you're Canadian. Can you speak like you're from Boston? Niyad, Naka. And you can all, depending on where you are, just by changing the subtle way that you pronounce syllables, you can make yourself sound a little bit different. In Vermont, you have to use less letters to say the same words, and add R's where they don't belong. Moving on. Okay, so this gets a little bit more, oops, sorry. Sorry. This way. That way. That way.
That way. There we go. This gets a little bit more complicated. Please note that the cortex wraps all the way around. So like, if we wanted to go find where your sensitive private parts are, they're actually along here somewhere. Right next to your feet for some reason. Maybe so you don't see other, well, see, there's a theory behind that. If people enjoy it, never mind. Okay, take human sexuality. Or don't, and just tippy toe away. Now, or don't tippy toe. That's wrong. Okay. So, but why? It's kind of funny that maybe it's so you don't defecate on your feet. Anyway, but there's a whole part of the brain, every part that we talked about before is the same on the inside. So the orbital prefrontal cortex right here is directly connected to this. What is this thing? The thing that connects everything together. That's something that's really important. The prefrontal cortex is actually called the anterior chamber, but it's the part of the brain that connects everything to the prefrontal cortex. There's something actually called a prefrontal lobotomy. Is when we go into the eyeball nerve, you slide an ice pick along the eyeball nerve, and then you do this with the ice pick. What happens to the brain right behind the eyeball? You cut it. You smush it. And by smushing this part of the brain, what does the person do? They lose themselves. They lose the ability to organize and plan behavior. By losing themselves, you take someone who's psychotic and make them not act psychotic. Okay? Okay? Sorry. So, if someone is psychotic, and I slice this part of the brain out, what happens? They become significantly less psychotic. Well, wait a minute. They're still psychotic, but they're not behaving psychotically. They just sit there. They're cured. Wait, are they cured? No. Yeah, you just missed that word from prefrontal lobotomy. That's exactly what we're talking about. Okay? So, but the idea that everything in your brain connects to this thing called the corpus callosum, and the corpus callosum connects to the center part right here, see this big thing? The center part right here and the prefrontal cortex. Everything connects to the prefrontal cortex. Okay, so now, part 2. This part in the center, oops, sorry. This part in the center, I can't draw on that. I have to click this button, then I can draw on that. This part in the center, I want to make this dark green. So you can see why this is really fun building this with clay. It's like in my physio class, we're going to make all of these pathways today with clay. Anyway, sorry. This is called the thalamus. The thalamus. That's really fun. The thalamus is right in the center. Okay? The thalamus, again, remember it's shaped like a little heart when we saw the slices down through it? There's a left side and a right side to it. The left side of the thalamus deals with the left side of the thalamus deals with the right side of the body. The right side of the thalamus deals with the left side of the body. Okay? When you take chapter 8 in my physio class, you realize that that's kind of a lie. Okay. So the thalamus is connected to the cortex, but what else is it connected to? To the spinal cord. So the thalamus is the relay system between the two. It doesn't do any thinking, but it does the relay. So, for example, you can see the eyeball nerve on here. Here's your eyeball nerve going in. Okay? Your eyeball nerve goes directly into the thalamus. Then it goes to the occipital lobe. It crosses over, of course, but it's a two-dimensional drawing, so I can't draw it crossing over. But so here's the eyeball nerve. It goes in right to the thalamus and then right to the occipital lobe, the UC. So now, this is really tricky. Wait, ask me again. Ask everybody else. I haven't told you the name of it yet. That's why I haven't said it. I didn't actually say it, but thank you. I'll tell you the name of it. Once we get all the parts together, we'll run the whole system through. Okay. So it connects to your spinal cord and that other cauliflower-looking thing. So now, but why on earth would I send visual systems to the center of the brain before I send information to the occipital lobe? Why not just send it directly to the occipital lobe? So it goes everywhere at the same time. This is really hard to visualize and hard to understand, but you'll understand when we start shouting at each other next class. But as the light information comes in, I'm going to write the word as here. As the information goes in, the information also goes out. It also goes out. It also goes out. So as the information is going to the occipital lobe, it's going to this part right here, which I'll label in a minute. It's going to the prefrontal cortex. Before you see it, it's going to the prefrontal cortex. What do you mean before you see it? Before your consciousness can understand what it is. Because that's what seeing is. Before you even understand it, there's another part which I can't, it's three-dimensional, so it's hard to draw, which I'm going to draw in this bright white color. Goes up like this around the cortexes. Color it in. This is called the hippocampus. So this white area right here is a cluster of cells, and it's called the hippocampus. It kind of runs on either side underneath the temporal lobe. So it's kind of outside of the main part a little bit. That's where your memory is. So the thalamus sits in the center. As you see something, the information is going to the occipital lobe. At the same time, the information is going to your memory. Your memory. At the same time, it's going to this little annoying spot, which I drew in Rainbow Sparkles last time, which is your, anybody remember the part? The amygdala. That's not fight or flight. Fight or flight comes from the amygdala is your, hey, you're afraid of that. Let me show you a picture. Oh, see, there's the new electrode after you printed it. So cool. Okay, sorry. So this little critter was chilling while we were mountain biking. My hand's about 2 feet away from him. He's big. I was going to pick it up, actually. I wanted to take a picture of it, but then it demonstrated that it did not want to be picked up. I don't know. Okay, fine. And I let it. Oh, I really wanted to get it off the trail, because it's right in the middle of the trail. Because my tire broke, and so when I was riding my bike, it was sitting on the edge of the trail. You can just see him. He's really cute. Okay? Anybody feel heebie-jeebies? You got some going right there. Oh yeah, I forgot about your spider phobia. I'm sorry. Okay, now. So what happened is, the second that image showed up on the screen, did you feel your skin crawl? You can actually let it go. But you should probably breathe. But so what happens is, before your visual processing system can even say, oh, the spider, what's your body doing? It's already activating your nervous system. This connection that goes down to the thalamus goes right to a part of the brain called the medulla. Which means the amygdala is involved, saying, hey, you're afraid of that. Before you are consciously afraid of it, before you even realize that it's a spider, your body's already telling away. My buddy Steve, that we go mountain biking with, I haven't mountain biked with him in years, but I saw him levitate. There was a rattlesnake on the side of the trail. And all of a sudden, his bike's on the ground, and he is like hovering about 4 feet away from it. I've never seen anybody move so fast in an entire life. I'm like, what? He goes, snake. I'm looking around, and there's like a little tail of a corner of a snake over there. It's like, how did he see that? He didn't process it, reacted to it. That's the key. The amygdala, the information comes into the thalamus, the amygdala needs to go, oh, this way is that thing. 70 other things pass by, amygdala, no, that one. We use the word in psychology called trigger. How do we know something is a trigger? Because it produces behavior prior to consciousness. So we talk a lot about post-traumatic stress disorder in psych because it is a really serious disorder. In post-traumatic stress disorder, what happens is there are some events in your hippocampus, remember your memory, that whenever you are even suggest something, you just start thinking about it, what happens? It triggers the amygdala to cause that wave of panic that you felt when you saw the critter. Is the wave of panic just looking at the critter the same as actually holding a spider? No, just saying holding a spider, she immediately started tensing up again. Are you spider phobic too? Yeah. So spider phobic means it causes a full panic attack. Means you just don't like spiders. So what's the difference between a panic attack and just not liking it? The level of severity of the symptoms. Like, I love dogs. I'm a big fan of dogs. And this big pit bull was hanging out of the car window this morning, and I was talking to the pit bull, like, hi, buddy. And the dog's like, someone's paying attention to me, yay! And getting all excited in the car and starts barking, and the owner's like, shush, shush. And I'm like, to the dog. If we could have a big pit bull, I would love a big pit bull, but anybody here have one? They stink. Yeah. I love this guy. at the dog wash. Will someone please get me out of the tub? He's just chilling there. It's like, all right, there's Fluffy Dog looking like an old lady. But I just love the look on its face. It's just... It's called Barkingdale's. It's just down the street from our house. The lady that owns it's great. There's a possum head. Yeah. This is one of my stat students got a new puppy for her birthday. So she brought it to class on a little blanket. It was so cute. No dogs on campus. Unless you're in my class, then I won't tell. Okay. That was just in the street. Just a possum head. It's so haunting. It's just cool. Yeah, just a head. Somebody ate the rest. Anyway. This is Sam. Sam's one of our friend's dogs at the beach watching volleyball. He's like, let me play volleyball. Let me play volleyball. And if he gets loose, he runs around and chases every volleyball on the beach. It's awesome. Okay. So, but if you're afraid of dogs, what happens? Yeah, as opposed to producing a positive emotion, your brain produces a negative emotion. So what do you think the amygdala and hippocampus really do? Memory and fear, but what do they produce? Emotions. Your emotions are connected from your thalamus, amygdala, and hippocampus, and there's actually one other part with your emotions, which I need to color in. I wish I had a brighter orange, but I'll use the skin color. Ew. Bad makeup color. Okay? This color right here, this part of the brain right here is called the hypothalamus. Sorry. Ran out of space. It's called the hypothalamus. What is the hypothalamus connected to? To the hippocampus. It's also connected to the, slightly connected to the amygdala, and it's directly connected to the thalamus. So the hypothalamus are your hormones. They're your hormones. This is a little bit of a lie, but, I mean, again, when you take more physical class, you realize how wide the lie. The hypothalamus really doesn't release the hormones. There's other parts of the brain that release the hormones. The hypothalamus controls the hormones. It signals the other parts of the brain to produce the hormones. So, for example, being awake or asleep is a connection from your hypothalamus to this area down here. Okay, which you can't see, so I'll make it darker purple. So this connection right here, this is called your pons. Today in class we're making, we're connecting the pons to the cortex in the video class. The pons take signals from the hypothalamus, which gets information from the thalamus to regulate arousal. Not like dirty time, like awake or asleep. So your pons sends signals to your cortex. So what if your pons sends GABA to your cortex? What happens? You've been doing this a bunch today. You're sitting there, you're like this, okay, I'm good. All of a sudden. Now, but it's funny, since the last 3 minutes, you haven't been falling asleep. Why? Now it's a spider picture. It's getting close to time to go. So because it's getting close to time to go, your thalamus is saying, hey, it's getting close to time to go. Because it's getting close to time to go, I need to rev up my physiology, so I got to go walk somewhere. So all of a sudden, your brain, you start producing glutamate with your consciousness. And what happens to that sleep you? But if you're sitting there in the middle of class, there's nothing going on that you need to pay attention to. Anyone know the cause of daytime sleepiness? Brace yourself. What's the cause? Not sleeping enough. Your pons keeps track of how much sleep you've got. This hypothalamus keeps track of the hormones you produce. If you get up in the morning and you still have sleep hormones called melatonin, guess what happens? You're more likely to fall asleep throughout the day. We went to like 7:50, and my wife got her laptop, and I just jumped in bed, and I fell right asleep. 7:50 last night. It was so awesome. The kids are like, what are you guys doing? Like being, oh, it's awesome. Well, I got up, I didn't sleep very well last night, and I had some wacky, crazy ass dreams. I love it. Anyway, so what happens is that if you haven't slept well one night, what happens the next night? Your pons send signals up to your brain to sleep more. Dreaming comes from the pons. Your pons breaks down some of the chemicals in the hypothalamus, and as it breaks it down, it produces a hallucinogenic substance, very similar to something called THC. THC is a fast-acting, short-lasting hallucinogen. And when you take these chemicals, it causes massive hallucinations that last for a period of time. These are called the gentleman's hallucinogens. You go skip at lunch and come back and have one in the afternoon. That suggests that you have heart problems. It's not important. Okay. But the thing about it is, the pons takes these chemicals and activates your cortex while you're asleep. So you dream, but if you had a traumatic event or you're stressed, you're thinking about the better up on the board. As soon as you go to sleep, who shows up? Because the hippocampus is located right next to all this stuff, and it totally shapes your routine. Okay, really quickly, I got 2 minutes here. So, this part back here is called the cerebellum. Again, this is recorded, so you can, I'll upload it right after class. Your cerebellum is the part of your brain that controls a very important thing called timing. This is why you wake up at the end of class, but in the middle of class you're tired. Even if you're not watching your phone or watch at the time, guess what it does? It keeps track of time. I do not use an alarm clock. I do not use an alarm clock. I wake up at 4 o'clock. I wake up at 4 o'clock every morning. And I can go back to sleep. That's why I go to bed at 8, 9 o'clock, so I get up at 4 to work. And then Tuesday, Thursdays, I do yoga in the morning by myself, because no one wants to do that. And then Monday, Wednesday, Friday, Saturday, I just wait. Sunday, Sunday. And so, but the thing about your timing is the cerebellum, notice how it's connected to your thalamus. It's connected to your spinal cord. It tells you when to produce certain behaviors. So for like the hardest part about shot putting, any moron can throw a shot put. The hard part is doing the full part. Because in order to spin around and time it, what happens if you get your timing off just a little bit? You're done. You break your fingers. If you get that timing off a little bit, your elbow goes like this, the shot put goes sideways off your fingers. Highly recommended for excellent finger pain. Hadn't had a good slam in the car door lately, throw a shot put wrong. Okay, next class we're going to build a brain. Please check out the chapters.